Welcome to lecture 4 of our solutions lectures. So I have put lectures 3 and 4 together because we are continuing the same concepts across these two lectures. So I have introduced to you some concepts around pKa and log P at the beginning of lecture 3, and in lecture 4 we'll continue this to look at pH partition hypothesis and drug absorption. Now, at the end of lecture 3, I introduce log P to you, where P is the equilibrium constant, partition coefficient that was introduced to you when we were doing our thermodynamics and equilibrium lectures. So it's a physical equilibrium concept, and it is it tells you the ratio of material that will be in an organic phase or an oil phase over an aqueous phase. So that ratio. And log P is the log of the partition coefficient. And we use log P to tell us about how we think our drug is going to behave in different systems. And this gives you an idea of what people would look for. So if you can see here, log P is increasing. So as you increase log P, binding to an enzyme and receptor will improve, aqueous solubility will go down, and so on. Absorption through a membrane, which we're going to focus on in this lecture, will go up, and other concepts of binding will go up or down. Okay. So that means absorption through a membrane will become better if you increase log P, but the aqueous solubility will become poorer as you increase log P value. So here we have a way of thinking about our absorption process, so absorbing across the membrane. And this is looking at lipophilicity changes with pH. So it links the concept of pKa that I spoke about before and how solubility changes with pH for weak electrolytes, with the concept of how easy or hard it would be for a material to absorb across a membrane. So first of all, let's look at a weak acid. So a weak acid will have the 50% ionized and 50% unionized when the pH of the solution equals to the pKa of that weak acid. And if you go to lower pH, then you're going to have more of the unionized form. And if you go to higher pH, you're going to have more of the ionized form in solution. If you go to lower pH and you increase the unionized form, as long as you still have enough solubility, you will then increase absorption across the hydrophobic membrane because you'll make your material slightly less water soluble and more lipid soluble, so more lipophilic. Let's look at the case for a weak base. In a weak base, we start at the center again, so where we have the pH equaling the pKa of our weak base, and we have 50% ionized and 50% unionized weak base in our solution. If we go to higher pH, we will then increase the amount of the unionized material in solution, and if we go to lower pH, we'll increase the amount of ionized weak base that's in our solution. So at the higher pH, you can see that that will improve our absorption across the membrane as long as we still have good enough solubility, because we will have the more of the unionized form, which is less water soluble, but more lipophilic, so more lipid soluble. So this is telling us where our where our active ingredient is more likely going to have a higher concentration of itself that is able to easily cross a membrane. So for a weak acid, you'd go for lower pHs, so maybe that would be preferred absorption, say, within the stomach. And for a weak base, you'll go for higher pHs, so maybe that would mean preferred absorption in the intestine, the small intestine. But that doesn't take into account surface area of the intestine and other factors that would lead to how a material can absorb. Okay, so that is known as the pH partition hypothesis that is used for weak electrolytes. And it's basically linking the lipid solubility to the structure of the material that is going to be more likely to be able to be absorbed across the membrane. What does this mean? So in the previous slide, I talked about the pH partition coefficient. And so let's look at that for our own example. So let's look at this where we have a weakly acidic drug, say with a pKa of 3. In the stomach, which we'll say has a pH of 1.2, that drug will be mostly unionized. Well, we would be able to work this out using the Henderson-Hasselbalch equation, where you would use the pKa as 3, the pH is 1.2, and it would give you the ratio of ionized versus unionized drug. And then that would allow you to work out the percentage ionization of that drug. We can do the same in the intestinal fluid, where the pH is 6.8. And in that case, it is higher than the pKa, which is 3. And the acidic drug would be totally ionized, or pretty much, because it would be 99.98% ionized. If you look at a weakly basic drug, where you have a pKa of 5, we can do the same calculations to work out how much of the drug is ionized in the stomach compared to the intestinal fluids. And you can see in this case, it will be 99.98% ionized in the stomach and 98.4% unionized in the intestinal fluid. So the pH partition hypothesis states that weakly acidic drugs are likely to be absorbed from the stomach, where the unionized form is more dominant, and conversely, basic drugs are unionized and will absorb in the small intestine. Now, the pH partition coefficient doesn't, or pH partition hypothesis, I should say, doesn't take into account the surface area of the intestine, which is significantly greater than the surface area of the stomach, and also the fact that drug spends a lot more time in the intestine. And in part 2, you will look at lectures that show that most absorption occurs in the small intestine for weakly acidic and weakly base drugs. However, the pH partition hypothesis does tell you how the properties of the drug differ and the impact that that may have on the ability of the drug to absorb in different areas of the GI tract. Here is a question that I would like you to have a look at, and I will go through the answer to this question later on a separate slides and in a separate document. So first of all, have a look at this lecture. You can pause the lecture and look at it now, look at this question now, or you can continue the lecture and try to do this question at the end. But do have a go at doing this question yourself before you look at the answer. So far in this lecture, we've looked at partitioning and the partition coefficients. which are important determinants for absorption and therefore therapy. So we can very easily understand the relative lipophilicity of our drug by knowing the log P of our active ingredient. And you'll return to that concept in a lot more detail in part 2 of this course. So don't forget log P, because it is going to come back to you then, and you'll need to understand what it is. We also learned that lipophilicity is not everything, and that we need to also think about some other things. So molecular size is important. Small molecules tend to absorb better than larger ones. And just to let you know the sizes, if we have paracellular crossing of the membrane, then 200 Daltons as the size of our molecule is about the maximum you can have. And for transcellular passive diffusion, so through the lipids, then 500 Daltons is going to be the limit. Dalton is a unit for molecular mass, and it's equivalent to grams per mole. So we also know, as well as molecular size, molecular structure is important. So although we're talking in terms of lipophilicity, remember that the reverse of this, or the inverse of this, is really solubility in the aqueous environment. And we need a balance of lipophilicity and solubility in an aqueous environment for our drug to be able to be absorbed at high enough quantities in the body to have the activity that it needs to have. So finally, for the end of this particular topic, before I talk about colligative properties, I'd like to introduce to you Lipinski's rule of 5 for determining drug suitability for oral delivery. So this is a simple rule, a set of rules that are all linked to the number 5, that lets you determine whether your drug molecule, based on its structure, is likely to be able to be used for oral delivery. So in other words, have a suitable, suitably cross the membrane for oral delivery. So these are the things. So we have, it needs to have no more than 5 hydrogen bond donors and no more than 10 hydrogen bond acceptors. Hydrogen bond donors are things like nitrogen-hydrogen and oxygen-hydrogen bonds within the structure that could donate the hydrogen into that hydrogen bond. And the hydrogen bond acceptors will have nitrogens and oxygens. And it needs to not have a molecular mass that is higher than 500 Daltons. So we know that from the previous slide, if the molecule is too large, it won't be able to cross the barrier, the membrane. And it needs to have an octanol water partition coefficient, so a log P that does not exceed 5. First of all, think about what log P means. So if you have a log P of 5, then that means that P, the partition coefficient, is actually 10 to the power of 5. So that means it's 100,000. So that means it's 100,000 times more soluble in the lipid environment than it is in the aqueous environment. If you go above that, you would be too hydrophobic. Okay. So remember that log P, a change of log P of 1, say going from log P of 1 to a log P of 2, is going from a partition coefficient of 10 to a partition coefficient of 100. So small changes in log P in reality do mean large changes in the relative solubility between the aqueous and non-aqueous environments. So those are 4 rules, all with 5 linked in them. So 10 hydrogen bond accepted is 2 times 5, of course. That can be used as a very quick measure of whether you think your drug is likely to be able to be formulated for oral delivery. Okay, to end lecture 4, I'm going to move on to a different concept that is important when thinking about solutions, and that's the concept of colligative properties. So when a solute, so our active ingredient, is dissolved in a solvent, some of the properties of the solvent changes, such as its boiling point or its osmotic pressure. And some of these changes do not depend on the nature of the solute, so the structure of the active ingredient doesn't matter, but does depend on the concentration of the solute. And these properties are called colligative properties. So colligative properties are properties that are affected by the concentration of the solute that's added to the solvent, but not by the identity of the solute. And examples of these are given here. So to explain colligative properties, I'm going to focus on the example of osmotic pressure. So osmotic pressure is the minimum pressure which is needed to be applied to a solution to prevent the inward flow of water across a semi-permeable membrane. So in other words, it is the pressure that would be required to stop osmosis. So if you think about osmosis as the movement of water from an area of high concentration of water to an area of low concentration of water, what pressure would you have to put on the membrane to stop osmosis from occurring? And that is the osmotic pressure. And this is the equation for osmotic pressure. This is not one that I would expect you to have to use in an exam. Osmotic pressure is proportional to the molarity of the solution, so the concentration of the solution, but there is nothing else here that is linked to there is nothing here in this equation that is linked to the chemical identity of the solution. Okay, and that's why I've showed you the equation. And this is what makes it a colligative property. It depends on the concentration of the solute, so the number of moles of the solute, N, but it doesn't have any terms that depend on any of the chemical properties of the solute. So R is the gas constant, T is temperature, and V is the volume of the solution. Okay, osmotic pressure is normally denoted by the symbol that's the same as pi. So here are a few terms that are linked to that concept. So isoosmotic is a way that you could define 2 solutions if they have the same osmotic potential. If 2 solutions of same osmotic potential are separated by our perfect semi-permeable membrane, then of course there would be no net movement of solvent between the 2 membranes. They would be, they would already be, if you like, at equilibrium. So they would be isoosmotic and there'd be no net movement of solvent. Isotonic is a term used for biological membranes because they are not perfect, and so they do allow some solute passage as well as the solvent passage. So if 2 isoosmotic solutions remain in osmotic equilibrium when separated by a biological membrane, they are termed isotonic. Okay, so isotonic is the term, sort of isoosmotic term for a non-perfect biological system. And this, of course, is very important for solutions for certain administration routes where you don't want to lead to swelling. You want to make sure your solution is isotonic, so isoosmotic with the surroundings. And this is what I am trying to show in this final slide here. So you can see that we have an isotonic material, that's very good. So in an isotonic situation, we have no net movement of water to and from biological structures such as cells. So we're in equilibrium and everything is fine. If you go to a hypotonic situation, which of course would not be so great, you'd be in a situation where you've got too much movement into the cells of water, and that would lead to swelling of those cells, and they would then just break apart. And if you go in the other direction, hypertonic, then you would have a net movement of water away from the cells. So here are some examples for drug administration. For subcutaneous injections, which is usually small volumes, so because they're such small volumes, isotonicity isn't so important. But if the solution is isotonic with the area of the body that you're going to add the injection, then there will be less pain on injection. For intramuscular injection, so you want to make sure that your solution that you're adding is isotonic with the biological environment where the injection is going to be given. And we should have isotonic solutions for large volume intravenous administration. And also for nasal drops. You might think it's also important for eye drops, but if you have the tears diluting the eye drop, then it's not as essential, even if it is desirable. Now, what can you use to shift the tonicity, if you like, of your solutions to make them isotonic? Well, you can add salts and sugars, and both can be used to achieve isotonicity. So you want the salt concentration of the solution to be equivalent to the environment, so that you're going to be adding your injection or administration. Now, during these lectures, we have gone through a number of different concepts. Not all of them I have mentioned to add to your glossary, but I would like you to continue adding terms to your glossary. And here's 5 terms from these lectures that I think are worth adding to your glossary. I'm sure you can think of a few more. And at the end of this lecture, you should know how to use Henderson-Hasselbalch equation. You should know what log P is and why it's important, and how ionization of a weak acetal base can affect solubility and absorption of drug into the body. What colligative property means, and I've given osmotic pressure as an example of a colligative property and showing the importance there.